Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. What I will be discussing this morning will be the measurement of alternating current voltage frequency using an oscilloscope. So, what I did is that I got a transformer here. The output voltage of this transformer is out here. It's alternating current. This one got no diode inside, so the output of this terminal, which is this one, is actually alternating current. So what I did is that I connected the ground terminal of the oscilloscope probe to this, and the signal terminal is actually this one. I set the volts per division to 5 volts per division, so we could say 1/2 of the graph of the alternating current. We just need what I call this, a clear view of 1/2 graph, just 1/2, because if we try to multiply 1/2, that will be one cycle. And I set the setting on the period of the cycle of the frequency under 1 millisecond per cycle. This is set to 1 millisecond per cycle. The unit of this one here is millisecond per cycle. So right now, since I placed the probe on the terminals of the output of the transformer, what's coming out on the graph of the oscilloscope is actually the graph of the alternating voltage. So for the counting to be accurate, I just place a 1/2 graph. This is from this point here till here. Okay? So I could count the number of divisions here from this point to this point. That's 1/2 of the graph. I could count the number of divisions here, and I could compute for the period of this one, because I got the setting on the time setting for the division. So what I will be counting here is that this is 1, 2, 3, 4, 5, 6, 7, 8. It's around 8.3. So from this point here to this point, that's a half cycle, right? And I could count 8 divisions. 1, 2, 3, 4, 5, 6, 7, 8. It's around 8.3. 8.3 divisions per half cycle. So if we try to bring out the calculation, if we will try to compute for the period of the half, for the, what you call this, whole cycle, half cycle is actually 8.3 divisions, right? So for the whole cycle, we will divide that, we will multiply that by 2. And that will be the total number of divisions for one complete cycle of the alternating voltage. And to compute for the total period of time per division, in seconds per cycle, we will multiply this by 1 millisecond per division. Where does this one emanates? It emanates from the setting here. Because when I set this to 1 millisecond per division, that's the graph of the output. And I counted 8 divisions from this point here up to this, and that is actually half cycle. Half cycle. So to complete the total number of cycles per or time per one cycle, we will multiply that by 2. So we'll go back to the computation. The number of divisions that I counted is actually 8.3. From the start to finish, that's half cycle. But since one cycle is actually 2 times that, we will multiply that by 2. So the total number of deviations for the whole cycle will be 8.3 times 2. Okay? And we will multiply that by 1 millisecond per division. So this division here, cancel with this. What will come out will just be simply the capital letter T here is actually the number of seconds per cycle. Okay? So if we try to multiply this one, 8.3 times 2 will be 16.6 milliseconds. And the unit of this one is actually per cycle. Okay? So 8.3 times 2, that will be the complete cycle number of divisions. So to complete the total seconds per cycle, we will multiply that by the setting 1 milliseconds per division. This is this one. When we set this to 1 millisecond per cycle, that's the graph. Okay, so our counting was actually based on the 1 millisecond time division. Okay, let's go back to the computation now. 8.3 half cycle, whole cycle will be times 2. That will also, the total divisions will be 8.3 times 2 divisions. And the setting is actually 1 millisecond per division, like what I said, this division here. Cancel with this. So if we try to multiply 8.3 times 2 times 1 millisecond, the total milliseconds, the total number of seconds per cycle is actually 6.6. This small letter m here is actually times 10 to the minus 3. So the unit of this capital letter here, the seconds per division is actually 16.6 times 10 to the minus 3 seconds per cycle. Like what I said, this small letter m represents times 10 to the minus 3. So the total period of the graph of the voltage across this, which is actually shown on the oscilloscope, is actually 16.6 milliseconds. So for us to find the frequency of the AC voltage here, the formula will be frequency is actually the reciprocal of the period. Okay? So frequency, the unit of this is actually cycles per second. So if we take the reciprocal of the seconds per cycle, what will come out will be cycles per second. So substituting capital letter T, that will be 1 all over 16.6 times 10 to the minus 3. And if we try to compute for this one by using our calculator, this will go up. So it seems our unit will be a 1,000. If this will go up, it will be 1,000 over 16.6. And if we try to bring out our calculator, the resulting value is actually 60 cycles per second. So the frequency emanating from this transformer that goes out here, the graph of the AC voltage is there, right? And we set the time setting to 1 millisecond per cycle. As per our computation, the frequency of the alternating current voltage is actually 60 cycles per second. And this is correct because right here in the USA, the public utility frequency is actually the one coming from the post moving to our houses is actually 60 cycles per second. So that's the way how to measure frequency of alternating current voltage by using the oscilloscope. Okay, I will repeat it before we will go for this morning. Okay, we connect the ground and the signal terminal of the oscilloscope, and we will be having a graph of the alternating current voltage. And for us to determine the frequency of this one, to be accurate, at least the graph will be steady and the graph will be big. So we could count the number of divisions from this point here to this. From this point to this point is actually half cycle. So whatever counting we will be having here, we will just multiply that by 2, and that will be the total seconds per cycle. And the setting of this one is actually under 1 millisecond per cycle. And as per our computation, I will repeat it, 8.3 divisions per half cycle, whole division will be times 2, the unit will be division, and we will multiply this by 1 millisecond per division, like what I said, division cancels, and the resulting value of the period per cycle is actually 16.6 times 10 to the minus 3 seconds per cycle, or simply 16 milliseconds per cycle. And to compute for the frequency is actually the reciprocal of the period. So frequency now will be 1 over capital letter T. And if we try to divide 1 over 16.6 times 10 to the minus 3, the resulting frequency of the AC voltage is 60 seconds per cycles per second. Okay? Good morning from Los Angeles. This is Professor David J. De Los Reyes.